Okay, let's review for Earth and space. I'm going to start out with basically move through the note packet or the notes that you've had right from the sun's path all the way to tides, and I'm going to move through it sequentially. Okay, so we're going to start out with this diagram off the front of your notes. We looked at this back in the beginning of the unit. Okay, we had to take a look at the observer's location 50 degrees north. So I'm going to find north, because Polaris is the North Star, and I need to mark where Polaris is. So that would mean Polaris is right here, okay? And I need to mark where the zenith is, okay? The zenith, if I had to look at this, zenith would be the highest point in the sky. So the zenith would be marked right here at 90, okay? Last but not least, okay, going back to the sun's path lab that we did, we have 50 degrees north. So the sun is always complementary to Polaris, okay, on the spring and fall. So I'm going to subtract 90 minus 50, and it gives me the noon path of 40. So I'm going to go due east. This is to create the spring path. Start at east, go up through 40, and then go down to west. And that's how I'm going to construct this, the spring and fall path. Remember, spring and fall are exactly the same amount of daylight because they're equinoxes. So it's the same days. March 21st, September 21st. Okay? So, moving on to the next one. Okay? You're going to need to be able to do, actually we're going to come back to that one. Alright, not going to work. So, continuing. A is at 0, B is at 75. So, really quickly, I have 75 degrees minus 0, which means, okay, and I need to do, or find out how many hours are between A and B. So, okay, 15 goes into 75 5 times, so it's 5 hours. So, if it were to be, say, noon at A, 12 p.m. at A, what time is it at B? I'm going to have to do 5 hours before that. So, and remember, and how we remember this, 8 o'clock Eastern, 7 o'clock Central. So, that tells me I have to move backward in time, move earlier. So that means I'm subtracting 5 hours, okay? So that puts me at 7 a.m. And that's how I find out the time in London versus New York City. That's how we need to do those time zones. Okay? So, continuing. Next thing. Okay, you're going to need to know the difference between rotation and revolution. Revolution works with the seasons. Revolution covers the year. Seasons and year. Rotation is the apparent motion of things through the sky. It is pendulums. If I see a diagram with regards to a pendulum, it's got to be rotation. If I see a diagram with what's called the Coriolis effect, okay, the Coriolis effect is the curving of the wind and the water as the Earth turns, okay? This would be a demonstrator, or this would be a diagram of the Coriolis effect. You don't have either one of these diagrams, so don't stress about that. But anyhow, again, the rotation of a pendulum, or the appearance of the rotation of the pendulum, or the appearance of things moving, okay, as they travel. That's the Coriolis effect. That's the Foucault pendulum. Pendulums are for rotation. So there will be a question on pendulum, there will be rotation. Already did that one. Talked about dome. So here's another picture of the pendulum, okay? So I had to imagine, okay, if I had a giant circle here, and here's the pendulum swinging, and I have pins around, like hours on a clock. As the pendulum turns, or appears to turn, it will knock down the pins. So, before I do the next one, where do you think, if it's going to rotate, okay, where is it going to knock down the next pin? It's going to knock down the next pin here, and here. Okay? Over a period of time, this is going to appear to shift, and that's what the pendulum does. Okay? So, continuing. Talk about that. Okay, let's talk about the moon. Okay, so we need to find out where the lunar eclipse is. So lunar eclipse occurs here. Lunar. Where's the solar? Solar is going to be here. Okay? Why? Because the sun's is being blocked out by the moon and it's putting the shadow on the earth. Okay? More lunar occur than solar because you have to be here to see the solar, but everybody on the earth, on this side of the earth, can see the lunar. Okay? The moon doesn't have a lunar and solar eclipse every time it goes around the earth because the moon is tilted at a 5.5 degree tilt. So you're not seeing that in this picture. Okay? Let's talk phases. What does this look like from the position of the earth? If I'm standing right here on the top of the earth, I'm looking at this. This looks completely shaded in. That's a new moon. If I'm looking this way, it's completely lit. It's a full moon. Now, we didn't go over this really well in class, and please pay attention. Okay, we did this in the lab, but I don't know if you got it. If I'm looking here, it looks like this. Just like the picture looks like there. But here, not so easy. If I'm looking at, if I'm here at the North Pole of the Earth, and I'm looking at the moon, in terms of a viewer, is actually in between the Earth and I. So what I have to do is I have to go upside down to look at it, because the person on the Earth is looking at it upside down in relation to me. So the moon's last quarter looks like this. Please make sure that you pay attention to that. Wait a second, Mr. Perry. How does it work that it's the opposite side that's covered, or the opposite side that's dark? Because you have to keep in mind that the viewer is looking at it from the opposite direction you are. So it's going to make it flip over upside down, like that. And that's why it looks like that. Okay? Phases of the moon. We also have no tides. Spring tides happen here. Neap tides happen here. But there won't be a question on that tomorrow in your Monday or Tuesday on your test. What's the shape of the orbit? The shape of the orbit is a slightly eccentric ellipse. Sometimes it's a little farther away, sometimes it's a little closer as it goes around the Earth. Let's see here. We're going to move on to the next piece. Oh, here's another one. How many days does it take to go from here to there? How many days does it take to go all the way around? Don't worry about it. Look it up in the reference tables. It's right there. Page 15. Okay. Next diagram. Eccentricity. Important one. You're going to have this. So, eccentricity works like this. I have to measure between the dots of the focus, and then I have to measure between the dots, or the length of the major axis. You will have to do this on your test. I'm providing you rulers because it's very important you know how to do this. Okay? So, I'm going to physically measure with my ruler in between the two foci. Right here. So it's going to come up to be 20. And then I'm going to measure the length of the major ruler, and it's going to be 50. So 20 divided by 50. Okay? 20 divided by 50. You'll calculate that out, come up with a number. It's always going to be a decimal. It's got to be between 0 and 1. Okay? So, this is the sun, and this is the orbit of the planet. Where do you think that planet is going fastest? Okay? So, if I have a position of 1, 2, 3, or 4, where do you think the planet is moving fastest? It's always going to be a 50-50 along the major axis. Mr. Perry, that looks really close. It looks like that, but remember, it's a tilted, it's coming out at you. It's a three-dimensional picture. So if I'm looking at the sun in position 1, that's where the planet's going to be moving the fastest. Because it's closest to the sun, the gravity's whipping it around. Whereas it's going to be going really slow out here. The sun is also going to have a greater gravity. at position 1. Where's weaker gravity out of position 3? It's going to appear to be bigger because I'm closer to it. Whereas it's going to appear to be smaller out here. Most of you guys do fine on the orbital motion stuff, but we've got to go over it just to make sure you got it. Okay, so that's orbital motion. It's also how you guys calculate okay. No, we're not doing that. Not doing that. Not doing that. We already talked about that. So rotation of the Earth, we have 24 hours a day here, 12 hours a day, 12 hours a night. North Pole is split by the sun's light, so that means that this day must be an equinox. Don't know whether it's spring or fall, but it's got to be spring or one of the two. Okay, here's a wacky one. Let's talk about this one. The lit portion obviously is the sunlight. The shaded portion is nighttime. So from our view, what day is what? Each one of these, well, not each one of these days, but they represent a special day during the year. Okay? So we have 4 days. We have our summer solstice, June 21st. Our winter solstice, December 21st. And spring and fall, same day. So one of these is completely fictitious because we only need 3 models. Okay? Or 3 pictures. So the first day, I started off with June 21st. Remember that the North Pole is completely in the light for June 21st. From these 4 pictures, which one is the North Pole completely lit up in? North Pole is completely lit up here. So this is the picture of June 21st. Okay? What about December 21st? Well, then this one, it's going to be completely dark in the North Pole. Bing! Number 3. Last but not least, spring and fall is when it goes right through the North Pole. I mentioned that about a minute ago. Right here. Spring and fall, straight through the North Pole. That means that this one's spring and fall. This one behind my head here, this one's completely fictitious. It makes no sense whatsoever. Continuing. Okay, so this was in our review packet, okay? So, want to go over this, okay? What dome is the farthest north? Without looking at the review packet, I'm looking at the stars. I find that this one has the North Star highest in the sky, so this one has to be north. Okay? Which one is the closest to the equator? This one has to be closest to the equator because it has the sun going through the zenith. And the North Star right on the horizon, so it's just barely on the northern hemisphere. Okay? We wanted to find out the time that the sun is. Here's noon. Here's 6 p.m. So the sun is right in between that noon and 6, so it's 3 p.m. Okay? Going over these things because they're going to be there. Going to be on the test. Okay, so here's a really good diagram. What season is this in? Well, it's not on your packet, but let's talk about it. What season it is? Well, if I'm looking at this, I immediately look to find out what pole is in the light. If I'm looking at this, the pole that would be in the light on this one would be the South Pole. So if the South Pole's in the light, it's got to be wintertime. December 21st right here. If we had to draw this picture in 6 months, what would it look like? Okay, here's the Earth. 6 months from now, the tilt never changes. Just where the position of the sun's rays are. So now the sun's rays are coming in from this side. The North Pole's in the light, the South Pole's in the dark. That's how I draw it. The equator never changes. The tilt of the Earth never changes. It's just the side that's getting the daylight. That's what changes because we're going around in our orbit around the sun. Okay? Questions on that? Not that you can respond. Anyhow, continuing. Okay. Whoa! Look at that. Again, same diagram. So where is the most amount? But this is now winter, spring, or summer. North Pole in the daylight. Got to be summer. Okay. We did this one in class, orbital motion 3. Okay. Where is the star look the smallest? If I look look at this, stars here, P4 is going to be the farthest away. Where is the gravity the strongest? Stars here, gravity is going to be the strongest at P2. If these shaded areas are an equal time frame, is there any difference between the areas? If it's an equal time frame in these shaded areas, that means that those pie pieces, those pizza pieces, will be the same area size. The time is always similar. Okay. Heliocentric, geocentric. Another big one. Okay. Let's talk about that one. How do I know heliocentric versus geocentric? Okay. Heliocentric is sun-centered. Heliocentric, sun-centered. Okay? So, I have the sun in the center. I need to find the sun in the center, the S in the center. Okay? So if I look at the sun in the center, okay, I have this one, but this one has planets going around the Earth. That doesn't work. Doesn't happen. Sun in the center. We have two of these. One here, wait a second. We have this one and this one. No, those are Earth centered. Sun is in the center of this one. But we have an object going around the Earth. Does that make sense? Well, if it's N for moon, then this would be a heliocentric model. Another heliocentric model would be this one. Sun with two planets and the Earth. That works. So either one of these, good examples of heliocentric models. Geocentric models, geology is the study of the Earth. Geo is Earth. Geocentric is Earth-centered. Okay? We look for the Earth's in the center. Earth's in the center on this one. So that's a geocentric model. Earth's in the center on this one and on this one. What season? Another question on this. Enough, Mr. Perry. Well, seriously, what season? North Pole's pointed away from the sun, so it's got to be wintertime. Back to the Earth and Moon. So which one has a solar eclipse? Position A. Which one has a lunar eclipse? Position C. Where is the sun, or where is the Earth's gravity strongest with the sun? Of these choices, C is, because C is closest to the 1.46. Where is the sun appear to be the smallest? Over here, when we're actually at summertime. Okay? So, that's what we're going to tie it up as, okay? And if you have any questions on anything that I just went over, please, please, please make sure you come into class and ask me those questions, okay? I think we're set. Okay.